All right, good morning. This is my last lecture, so I want to thank you for your attention and especially for your questions because they do make the lecture more lively, and it does help me find better ways to explain things and also understand. Some of your questions were very insightful and actually made me think differently about things that I'm talking about. So thank you very much. And are there any more questions? All right. So today I will talk about the second part of my topic, which is heavy ion collisions. And if there is only one thing you want to know about heavy ion collisions, I thought, what should that thing be? And it seems to me that you need to at least know about the Bjorken's model of heavy ion collisions. It's by far the most influential paper in the field, with almost 3,000 citations, and it's a very elegant and simple, if not simplistic, model of heavy ion collisions, but it very much underlines the common lore and even the language and terminology which both theorists and experimentalists use. It's, in a sense, it's a starting point or zero sort of approximation to this complicated process which happens during the heavy ion collisions. So I will talk about the Bjorken model, and in the using it, I will try to describe what heavy ion collisions are. So Bjorken. So essentially, it's a model which assumes validity of hydrodynamics. So that's essentially what it is, supplemented with a certain clever assumption about the initial condition. And after that, you get that simple model. So what is a heavy ion collision? Claudia Ratti already described. Well, obviously I have to repeat some of the basic. It's a well, two heavy ions or heavy nuclei colliding. They're ions because experimentalists, of course, are trying to strip as many electrons as possible, but there are always some imperfections, so they carry a little bit of once they're charged, they can be accelerated and collided. Typically, well, there's a whole range of collision energies. We will be interested in the situation where the nuclei are ultra-relativistic, so the gamma factor is much bigger than 1. And the collision, well, the system just before the collision, if you take a snapshot, looks basically like this, right? Because of Lorentz contraction, this is roughly the radius of the nucleus, which is something like 7 Fermi or so for lead or gold, divided by gamma, right? And so they move practically with velocity of light towards each other and collide. So what happens after collision? Well, that's the most difficult part, or the least understood, I would say, part of the heavy ion collision. So what we know, essentially that was assumption of Bjorken. Well, he wasn't the first to make this assumption. It goes back to Landau, who was the first to assume that the result of collision is some thermally equilibrated matter, right? So, and that's the assumption under which the whole field is operating. So nuclei collide. Some of them go through. So there is a residual kind of Swiss cheese which is left after the collision going this way, and the similar this way, right? They still go with velocity of light. So v is for the 1, this way and this way. But what we do study is what they leave behind. Some of these collisions produce particles which move in the directions perpendicular to the motion of the initial projectiles. They collide, and these products of these collisions. And if the density is high, which is what happens in the heavy ion collisions, they thermalize rather quickly. So this is this medium inside, which is Bjorken wants to discuss. Now, how this process happens of equilibration, that's the open question. We really don't know how exactly that process occurs. What we do know is that at the end, what we see looks very much like a thermal medium, which has undergone some expansion. So I will not discuss this topic. There are, of course, it's not completely unknown. There are quantitative descriptions of this process, but there are several different ones, and they cannot all be true. So that's sort of the problem. And of course, one of the open questions is from the observation, we see that the thermalization has to happen very quickly. And if you just estimate using the, gluon cross sections of reasonable size, that simply cannot happen. So there has to be some mechanisms which we do not yet know how to describe adequately, which lead to that observable effect. Notwithstanding this, once the medium thermalized, yes?
The gluon cross-section is too low?
Too low.
Okay.
Yeah, too low. Or in other words, maybe the gluon cross-section is too high, but then can you talk about gluons if their cross-section is so high, right? It means that either if you want these cross-sections to be too high, then these gluons basically do not have any mean free path to talk about, and therefore this is not really a medium which could be described in terms of particles. In fact, one of the contributions of the this gauge gravity duality to the field of heavy ion collisions is that it's for the first time allowed us to have a model. It's not exact description of these theories are not QCD, but they allow us to describe the evolution of a system which cannot be described which is thermalized, but it cannot be described in terms of scattering particles. So it's not a rarefied or weakly interacting gas. It's more like a liquid, right? And we can describe it not only in the hydrodynamic stage, where it doesn't really matter what the underlying, but actually pre-hydrodynamic stage can be also described. It's a microscopic ultraviolet complete description, which does not assume, in fact, it's a small coupling. In fact, it assumes the opposite. It's the more strongly coupled. And in fact, in this description, we can actually see that thermalization happens very quickly on a scale if you normalize to the scales of QCD, this model's on the scales of a fraction of a Fermi, fraction of a time that the light takes to traverse the proton, right? So, but of course the problem is that, so we know this happens, but what does it mean to say we know how this happens, right? All right. So basically, we understand that this must happen, but really a satisfactory description of this process is still an open question, right? Okay. Once the thermal equilibrium is established, then we can describe the system hydrodynamically, and that's what Bjorken does. So then you can think of the system in terms of the local energy density, local baryon density, and local velocity, right? The flow velocity. So each region here carries a certain velocity. So if you look here, and calculate the total energy and total momentum, you divide the two, you get the velocity, right? So it moves with some velocity v in this direction. The regions here move in this direction. If you wish, you can plot as a function of z. So imagine I took a snapshot now of this. So the velocity at each end is equal to 1 and minus 1. So this is vz. Z is usually chosen to be the direction, the beam direction, minus 1. And so velocity obviously has to vanish here, and then in between it does something like that, right? Now, so what the Bjorken scenario, or that's how it's usually referred to, a Bjorken model assumes, is that, well, that's not how Bjorken phrases it, but it's convenient to look at this picture and say that what it assumes is that this dependence is just linear. It's obviously the simplest choice, right? But it has other important so in Bjorken way of characterizing. So in Bjorken scenario, it's linear, and it's a reasonably good approximation to the reality. Yes.
For which time is it? For which time is this plot valid?
The time equal to that distance divided by c. You know, they go further apart.
This is a space coordinates.
Yes, this is a spatial coordinate.
It should evolve with time, no?
Yes, they evolve with time. These lines go further away, and the slope gets smaller.
So
right.
This is z over t. Kind of.
It's a snapshot at the time of your choice. So you give me the time, I draw you the picture. It will always be like this. The only difference will be what will be that number. It will be that time multiplied by c, right? But it's always linear, and it turns out that this assumption corresponds to another property of this collision. If I view the collision from a different frame, so instead of in this case, I'm viewing this from the lab frame where the two nuclei have the same gamma, right? But I can boost, I can view it, I can imagine view it from a different frame. It would look the same. So it will still be linear, except of course 0 will be somewhere shifted. So that boost invariance is the assumption that Bjorken makes, right? One can understand why this is a very useful assumption, because if you assume that at some point, like the initial condition is boost invariant, equations of hydrodynamics are boost invariant, right? I mean, they are Lorentz invariant, right? So therefore, if there's a boost invariance at some initial time, it will be preserved in the solution. So Bjorken's solution is essential to hydrodynamic equations, essentially a boost invariant solution. So let me now write some formulas which describe what I just said. So let me see. Maybe I should better use these notes here. So as I said, velocity, or z component of velocity, is equal to z divided by t, right? That's the. So now let us, well, obviously, the other assumption is that all the motion is only longitudinal. Of course, that assumption cannot be true in hydrodynamics, but Bjorken says, let us first assume that these nuclei are infinitely large in the transverse direction. We can relax this assumption later, but that's essentially Bjorken scenario starting point. So let us write so Vx equal Vy equals to 0. So since we're talking about Lorentz and boost invariance, it's convenient to introduce the full vector velocity, right? Full vector velocity, its components uz or uz is Vz divided by square root of 1 minus v squared times gamma, right? So if we use that formula, since there is only one component, this would come out to be z divided by square root of t squared minus z squared. So this quantity here is a proper time, right? You can think of it as a proper time for the interval between events separated by time t and distance z, right? So this is the proper time, and often in this context is refers to as Bjorken proper time, right? So it's a proper time. So uz is z divided by tau, and ut is t divided by tau. You can easily see. So that ut squared minus uz squared is equal to 1, as it should for the full velocity. So what is convenient, useful observation here is that if I write this as a full vector, then it is equal to gradient of tau. Just easily can see that, right? Which basically means that if I draw space-time diagram here, t and z, so this is my light cone. So the line of equal proper time is a hyperbola, which looks like this, right? It's some tau equals constant line. Well, the velocity is always normal to this line. It basically means that points in this direction of this ray. You can think about it. This is hyperbolic geometry. It's Minkowski space. So what in Euclidean geometry was orthogonality between the circle and the radius, right? Here, the orthogonality is between the hyperbola and the radial line, right? So this is the vector which you get if you take the gradient of tau, right? So for different tau, you get different lines, right? So there's lines of constant proper time, right? And this radii always cross them, right? Are always orthogonal to them in that sense, right?
It's orthogonal in Minkowski metric.
In Minkowski metric, of course, yes, right? Which follows just from that, right? Because this vector is always orthogonal to a curve of constant tau, right? If you move in the direction of constant tau, it's obviously tau doesn't change, and therefore the projection of u mu in that direction must be 0, right? That's what orthogonality means, right? Okay. So in other words, you can say that if you just follow the world line trajectory of each element of that fluid, right? It just follows that line, right? Just follows this line, right? It is convenient to introduce different coordinates here. Instead of coordinates being like this, which are orthogonal, there's a natural other choice. These are the surfaces of constant tau and the ones which are perpendicular to them, which is the surfaces of constant velocity, right? Or even better, rapidity. So if you remember what rapidity is basically hyperbolic arctangent, right, of velocity, right? That's what rapidity is. Or, since it's hyperbolic function, you can write it as a, in terms of logs, right? So the transformation between the Cartesian coordinates t and z and Bjorken coordinates, so this is line eta equals constant, is, well, I've written already, it's here. So since Vz is equal to t over z, right? So it's 1/2 of log t plus z divided by t minus z, right? So, and tau, as we already have seen, is square root of t squared minus z squared. In this way, the transformation, and of course, you can also write it this way, z over t. Perhaps a little bit more intuitive if we write transformation, inverse transformation. So then z will be equal to tau times sine hyperbolic of eta, and t is equal to tau times cosine hyperbolic eta. So you can see that t squared minus z squared is equal to tau, and t divided by z, z divided by t is a tangent, right? Hyperbolic of eta, right? So it's easier to see it this way. And from that, again, you can see that there's analogy with a radial polar coordinates, right? So if you replace this with ordinary sine and ordinary cosine, this will be the radius and this will be the angle, right? So, so this variable is called Bjorken rapidity. This variable is called Bjorken rapidity. So note that Bjorken rapidity is really a position variable, not velocity variable. Usually rapidity is defined just as just another measure of the velocity, but remember there is just a linear relationship between velocity and position, right? And so in the Bjorken, so Bjorken rapidity is just a spatial coordinate, right? Okay. So now let us look at equations of hydrodynamics. So as you know or should know, equations of hydrodynamics are essentially conservation equations for energy, momentum, and a charge, right? in a local form, they correspond to a local conservation of corresponding currents, right? For example, charge conservation is expressed by conservation of a charge current, and the energy momentum conservation is characterized by 4 equations, which is a conservation of stress energy tensor, T mu nu, right? So let me begin with the current conservation first, because it's easier. So let me introduce N, which is the density of the the density of the charge in a frame in which the current is 0. Right? The density is not a scalar. It's a force, it's J0, right? It's a force component of a current. But there is a once we have a vector of the current, there is a frame. You can choose a frame in which this vector is just time-like, doesn't have spatial component. There is no current flowing, right? So that we can always go into this frame, and then N is the charge density in that frame, right? Then, of course, current is equal to N times U mu, where U is that velocity of that frame, right?
That frame can be accelerated, no?
We're always talking about inertial frame. There is no general, it's just inertial frame.
But I mean, the density can be kind of fluctuating or accelerating in that process, no or not?
Yes. In principle, yes. But let's just look at the snapshot. At a given point in time and space, we can ask, what is the current? Remember, current is a function of event, a point in space-time, right? So for that given point in space-time, we can define N. We don't care what happens afterwards at this point, right? So then by Lorentz invariance, this should be the current in any other frame, where U mu is the velocity of that element, right? So therefore, this equation looks like this. Right? And, well, I can write it, out. It's U dot D times N equals minus N V dot U. Right? It's the same equation. And let me look at this equation and say, what does it say? Well, it says that, well, what this U dot D means? It's a time derivative minus, well, you can think about it in 2 ways. You can think about it, and the easiest way is to go again in a frame in which, whose velocity is U. Then this is just time derivative, right? So in that frame, the density changes. Well, you ask, isn't charge conserved? How can the density change? Well, it's the charge is conserved, but the density is charge divided by volume, right? And if the system expands, the density has to drop. And that's exactly what that says. And the rate of expansion is d dot u. It's a divergence, it's divergence of the velocity field is the rate of the expansion, right? And so it just tells you that that it just dilutes the density exactly as the conservation requires. Okay, so that's the equations of hydrodynamics here. And for T mu nu, again, we can define the energy density as, again, it's T00. So energy density is not a scalar. It's not even a component of a 4 vector. It's a component of a tensor, right? 0, 0 components of. But we can always, again, go to a frame in which the, let's say, momentum density is 0, right? That's what is called Landau frame. And then declare epsilon to be the energy density in that frame, right? Then by Lorentz invariance, similar to this argument, you can conclude that, right, when the stress energy tensor should look like this, plus some arbitrary contribution whose 0,0 component vanishes in that frame, right? So it has to be some symmetric tensor, and obviously has to depend only on that frame, right? Because the components of it has to vanish, and it's easy to construct such tensor. Delta mu nu equals to G mu nu. And here I have to write it first and then apologize later. The sign here depends on your signature choice for G mu nu. So I'm sure that you are used to the signature choice in which G00 is +1, right? G00. In hydrodynamics, it turns out this is least convenient choice. It's less convenient choice than the opposite one. So -1. So sorry about that. This is the choice, and we are not going to use it that much. But I just want you to be aware that in papers on hydrodynamics, this is a preferred choice. Again, it's not uniformly accepted, but it's very common. If you want this to be +1, then it will be minus here, right? So this is the projection. If you wish, it's a projector on the space of on the spatial directions in that frame. In that frame, in which in the Landau frame, in which whose velocity is u mu, right? For velocity. So this is the tensor, and if you substitute it into this equation, your equation can be written in this way. Well, there are obviously 4 equations, so let me write them. I don't need that. So one can be written like this. Right? So that equation obviously looks very much like this one, right? And of course reflects the conservation of energy. So the rate of change of energy is proportional to the expansion rate, right? And this factor, this term epsilon is easy to understand, is the same as this one, right? But pressure, this term. So what happens? Well, we already understand that energy is conserved, right? But the energy density is not, because when the system expands. But that would explain only minus epsilon times expansion rate, right? What does this term do? Where does this come from? Why it doesn't violate the energy conservation?
Doing work.
It's doing work, exactly. Remember that, yes, the energy is conserved, but it could be exchanged between 2 systems, in this case, neighboring cell, right? And that's what we call work. Work is the exchange of energy. So if the system expands, it does work proportional to the rate of expansion per unit time and pressure. And that, of course, depletes the energy as well. These are the 2 terms which are very easy to identify. And finally, remember there are 4 equations here, and the remaining 3 are the equations for the 4 velocity. This is also easy to understand. This is basically Euler equation, right? It basically says that acceleration which is, well, why there are three equations? Because not all four components of U are independent. And this is the rate of change of velocity, which is acceleration, right, in the local frame, local rest frame. And this is force. So it's just a Newton's law, right? You can see that because of this projector, this in the rest frame of the fluid, this is really spatial gradient of the pressure, right? Only spatial gradient. And right, okay. So I'm sorry, W is just a common notation for epsilon plus P because it appears very often. Okay, so this epsilon plus P, also known as enthalpy, appears quite ubiquitously, and then this equation basically plays the role of mass density, right? In the relativistic hydrodynamics, it's a mass density. Okay, that's what as much as you need to know about relativistic hydrodynamics in the for Bjorken expansion. Of course, you may notice that nowhere here the diffusion or viscosity appeared. So this is the ideal hydrodynamics. And you are wondering, so where is it? You know, right, where would be? Well, there are several subtleties which we ignored. For example, the velocity in which the momentum vanishes, which we called u mu, is not the same as the velocity at which the current vanishes. There could be a difference, and that difference is related to the diffusion, essentially. So there are, following Bjorken, we will neglect this just to demonstrate the basic features here. Okay. So now let us write these equations for the Bjorken flow. We know what U is, right? So in order for this equation to satisfy, so we have to substitute here. It's easy to see that U dot D is essentially derivative with respect to tau. You can do this. And also the rate of expansion, which you can also calculate using this, right, is just 1 over tau. If you're familiar with Hubble expansion, which I'm sure you are, this is somewhat similar, right? So the rate of the expansion is inversely proportional to the age of the system in proper time counted from the initial singularity, right? So you can think of tau as a Hubble time, except that this Hubble expansion is one-dimensional, right? If you need more connection with Hubble, just look at this, right? This is exactly what Hubble would say, right? The velocity is linear with the distance between the two. So the further the two objects are, the bigger the difference in their velocities. That's roughly speaking. All right. Well, then the first equation can be just written as the derivative with respect to tau is equal to minus epsilon plus p divided by tau. The equation for charge density is minus n divided by tau, right? And you can see the right-hand side doesn't contain any, only contains the variable tau, not eta, right? So if the initial condition, for example, for n is eta independent, which means boost invariance. Remember, eta is a rapidity, and the rapidity changes additively, right? So no dependence on eta means boost invariance. Then this equation will preserve it. And so will this, assuming that P, of course, is a function of epsilon and n. So if both epsilon and n are initially or at some point in time independent of eta, then they will remain independent of eta. That's what Bjorken observes. And therefore, equations simplify very much. Instead of having a partial differential equation, we just have an ordinary differential equation for just one variable. The only thing we need to supply is the equation of state. And then we can solve that equation. Yes?
How does this, is this assumption consistent with thermal equilibrium?
The answer is unequivocally yes. It's an assumption which requires the assumption of thermal equilibrium. I'm not sure why you're asking.
Because usually then V is Boltzmann, the Boltzmann distribution, no? And I mean, now we're saying that V has this very strict dependence with space.
I think when you talk about Boltzmann distribution, you talk about different velocities. So when we talk about V here, in hydrodynamics, it's a macroscopic velocity. It's a velocity averaged, if you think about in terms of the gas, of the Boltzmann gas, it's the average velocity of the particles. While when you talk about Boltzmann distribution, it's a statement about distribution of velocities. So there are two different velocities involved in this case, right? So for example, for a medium in a box, the hydrodynamic velocity is 0. It's not moving anywhere, right? But of course, the particles in the box move with velocities which is basically given by Boltzmann distribution. Is that answers your question?
Yeah.
Right? It's just, that's how you need to think about it. Well, of course, this equation also is automatically satisfied because if P, notice that this is a spatial derivative. So it's essentially derivative with respect to eta. If you calculate it, it's, and if P does not depend on eta, right? So in other words, if pressure along the, well, energy density and charge density, and therefore pressure is constant on that line, then there are no gradients along this direction, right? And therefore no acceleration in that direction. And that's what is required in order for each element, fluid element, to move along a straight line. So that equation is automatically satisfied as well. So that's essentially the equations which describe the Bjorken solution. The only thing which is left is just to substitute equation of state, initial condition, and you get the, right?
Sorry.
Yes?
You said, so going back to this question, you said that it's in equilibrium, but I expect that to cool down because it's expanding.
Yes.
So it's not in equilibrium.
At some point it won't be. Yes. I will get to that. Right? I'm getting to that. You are just anticipating what I was going to say. So another quantity which needs to be understood is the entropy. Well, as you know, because we neglected dissipation, ideal hydrodynamic equations conserve entropy, right? It's easy to see by calculating, by writing equation for the entropy, right? So, well, it's remember that entropy is a function of energy density. Entropy density is a function of energy density and charge density, with notations which we introduced in the previous lecture. So this should be beta u dot d times epsilon minus alpha u dot d. And so the evolution of epsilon and n is given by these equations. So if we substitute them here, right, we'll find minus s d dot u, right? Where we used the relationship between entropy and so it's right? You can check that this corresponds to the thermodynamic relation that you know, okay? So, and comparing it with the equation for the charge, you can see that entropy is conserved in the sense that it only changes, the entropy density changes exactly as the system expands. So therefore, for the entropy, we can write this equation, right? Yes?
So there in the lowest line, it's minus alpha dn, right? So it's the differential of the charge density. Yes. Dn, right?
Dn, yeah, it is n. It looks like u, right? Yes, n, of course.
And you didn't write the pressure term in the differential, right?
Well, there is no pressure here. ds by dE is 1 over t, and ds by dn is mu over minus mu over t. There is no pressure. Pressure comes in here from this equation. This equation is epsilon plus p equals ts plus mu n. This is just rewritten in this way, all right? And pressure comes from the equation from E.
It's already density.
Right. Yeah. So you can think of in this point of from this point of view, pressure is a Legendre transform of the entropy, right? So S minus beta E plus alpha n is equal to minus epsilon d beta plus n d alpha. So that's it. You can see that this is beta times p, right? So that's just rewritten in a different way. So the entropy is conserved. It means that the system expands, the entropy density drops, and drops in a very simple way, so that S times tau is fixed, right? So if S is a density per unit volume, S times tau is a density per unit rapidity per unit transverse area, right? So it's so it drops, and so basically entropy is some initial value at initial time divided by time, right? So, and that's at that point, Bjorken could estimate what the initial temperature is, provided, of course, you know when thermalization happened, right? What is the thermalization time, right? If you know the number of particles produced, you can estimate the entropy, right? What do you need to know? Well, you need to know how long does this expansion last before before hydrodynamics breaks down. So for that we need to discuss what happens and what limits the expansion. So, and by the way, so for example, it's in a sense it's also very similar to cosmology. If you assume massless equation of state, like quarks, think of quarks and gluons, then entropy is proportional to T cubed, right? And from that, since entropy is 1 over tau, temperature should drop as tau to the power 1 minus 1/3, right? So that's an easy estimate one can make. So it gives us the idea of what happens during the collision. So now let us, well, this expansion cannot continue forever, and the reason is mostly because, well, first of all, the energy, as you pointed out, the density drops and at some point, the assumption of thermal equilibrium requires that the system equilibrates to the new temperature quickly enough, right? But the equilibration rate is basically determined by the collision rate in that system. Well, as density drops, collision rate drops as well, right? And at some point, the if the collision rate drops below the expansion rate, the system freezes out. It's exactly the same terminology is in a cosmology, right? And after that, there is no change of either chemical composition or momentum distribution because there is no scattering. And what we see is a snapshot of the system at freeze out, right? So what determines the time of freeze out? Well, there are two kind of important features. First of all, one of them, and it seems to be the kind of manifest in the experiment, is the phase transition, or rather crossover. So as degrees of freedom change, right, the hadronic cross-section, especially inelastic ones, which lead to change of the well, inelastic one, which change the chemistry of the hadrons. Those cross-sections are much smaller than the cross-sections in the quark-gluon plasma, which could create quarks, for example, therefore changing the chemical composition. So there is if there is a sharp crossover, there is a temperature at which the inelastic rates suddenly sink. And at that point, the chemical composition falls out of equilibrium. That's the chemical freeze out. And that's our present understanding of why that temperature, which can be measured by basically looking at the chemical composition, that is the ratio of particles with different, for example, baryons to pions, etc., or with different masses, why this temperature is very close to the temperature which of the crossover, which we know from the lattice, right? So that's one reason. So the collision rates drop. The other reason, which is the one which also Bjorken discusses, is well, the transfer size of the nucleus is finite, right? So in principle, if the nucleus was infinitely large, it would think about it this way. The reason that the freeze out is possible is because the particles can escape the system without scattering again. But if the system is infinitely large, it will never escape. So the system will cool forever, right? Well, think of a neutron star, right? It cools, you know, to zero temperature if you wait long enough. So the other reason that transfer size matter is, well, this has to do with violation of Bjorken assumption, which is that the expansion is purely longitudinal. it isn't, right? Because there are gradients of pressure which are transverse to the longitudinal expansion direction, simply because, well, there is some matter inside this disk and there is none outside, so the pressure just drops at the edge of that system, right? Well, hydrodynamics, what does the hydrodynamic do with a sudden drop in the pressure? It's a shock wave. Shock wave will propagate, right, towards the center of this disk, right? The velocity of the propagation of a shock wave is essentially sound wave, sound velocity, right? So we can estimate how long it will take for much of the medium to be affected. What? For the shock wave to reach the center, at which point you can no longer talk about longitudinal expansion, because the estimate is the radius of the nucleus divided by speed of sound.
So can you repeat how this shock wave is produced?
So the pressure as a function of radius, radial coordinate, looks like this, right? And well, that shock, right, propagates inside.
Okay.
So in other words, at a later time, you would see something like this. So the matter, right, the matter here expands faster. Think about it this way. Because there is a large gradient of pressure, there are very strong forces pushing on the medium outside of the shock wave. So while the medium inside doesn't know anything yet about incoming shock wave, right? Because and so it still expands longitudinally, but the matter, well, except for maybe small gradients here, which we are neglecting, the matter outside of the shock waves are already expanding in transverse direction. Essentially, a good approximation to what happens is that expansion at that point becomes three-dimensional, right? So it's essentially an explosion of, right? So that kind of Bjorken picture can last only over this approximately this time, right? So if the radius is about 7 Fermi divided by, 1 over square root of 3 or so, you get something like 10 Fermi. This is the order of magnitude of the time during which this Bjorken description works. Well, of course, Bjorken description doesn't necessarily breaking down doesn't mean necessarily that the system must freeze out. But remember, three-dimensional expansion dilutes the density even faster. So in practice, once the three-dimensional expansion sets up, the density drops precipitously and the freeze-out occurs. So typically, this is basically 10 to 15 Fermi is the time between the initial equilibration and the collision. And that time, being much bigger than the typical equilibration time or typical hadronic scale of a fraction of a Fermi, is what justifies the hydrodynamic description here. That sort of gap in the scale. Obviously, it's not as good as in condensed matter, where the typical size of the wave is huge compared to the let's say typical interatomic scales or mean free path, even for gases, right? Well, that's the life in the field of heavy ion collisions. You get this scale windows which you would like to be infinitely large, but it turns out to be just an order of magnitude, or sometimes even factor of 3. This is the kind of level of description. Yes.
The equilibration you're talking about is thermal equilibrium, right?
Thermal as well. Yes, thermal.
Because chemical equilibrium.
And chemical. So I kind of conflated the two, although not completely. I did mention that it's a chemical rates which drop. The scattering, which is elastic, which changes the momentum, have different cross sections. Well, some of it, many of those cross sections drops, but there are some which still remain large, in particular because of the resonances. The most prominent one is the most abundant particles which you see after the freeze out. Given that it's a thermal gas, what should you expect will be the most abundant particle? Pions. Why?
Are the lightest,
Hmm?
They are the lightest.
They are the lightest, and the Boltzmann factor for them is the largest, right? So pions are the, so it's basically, and the larger the collision energy, and the larger is the initial temperature and the initial entropy, the larger is the proportion of pions, right? Because pions basically are the particles which carry most of the entropy. That's part of the reason why when you increase the collision energy, chemical potential drops. Because whatever baryons are stopped in the central regions are diluted now by a larger number of pions. So that reduces the chemical potential. Remember, density is exponential of mu over t. Right, I was talking about the kinetic freeze out. Pions, the scattering of pions is not very effective. They are goldstones, so they don't scatter that much. Well, they do have a resonance, though, which is rho meson, which turns out to be at an energy which is close to the typical energy of the, but more significantly, pions also scatter on nucleons. And there is a delta resonance, which is right where the thermal, where the freeze-out temperature is, right? So the typical energy of the particles at the freeze-out temperature is. And that prolongs the stage at which the hadrons are still scattering with each other. But this scattering is elastic, or rather, I would say quasi-elastic. Pion and proton can produce neutron and charged pion, so it's possible to change composition, but only in this sort of isospin exchange way. This is what is called quasi-elastic collision. So the temperature corresponding to which you extract from the moment of the particles are usually slow, are usually lower than the chemical freeze-out temperature. Right.
So the Bjorken description is valid till kinetic freeze-out? Or chemical freeze-out? Or?
That's a good, typically, yes. That it is typically valid until kinetic freeze-out, but it is more like a coincidence, because at the time when kinetic freeze-out occurred, at that time already the expansion becomes three-dimensional, right? But the breaking down of Bjorken expansion is not due to the kinetic freeze-out. In fact, you can think of kinetic freeze-out is still a process which essentially changes the equation of state of the system. Some processes are no longer able to equilibrate, but there is still some thermal equilibration. So we can talk about what is called partial equilibrium's equation of state. So people do this. But this already happens independently of that. The onset of the transverse expansion already breaks the Bjorken assumptions at that point, right? So now that we know what the typical freeze-out time is, 10 Fermi or so, right? Now, if we also, as Claudia Ratti described, can determine the temperature and the entropy of the system at freeze-out, right? So we know this. Right? The only thing we need to determine the initial entropy and corresponding to the initial temperature is the initial equilibration time. Right? Well, because of that feature is the biggest unknown. We don't really know how equilibration happens, but there are ways to access this information, and you get somewhere between 1/3 maybe to 1/2 Fermi or so. Let me put about 1/2 Fermi, right? So with this information, you can determine the initial entropy, and correspondingly, assuming equation of state of quark-gluon plasma, or the one from the lattice, if you wish, you can determine initial temperature. That's how we know, essentially following Bjorken's prediction, that initial temperature is somewhere around 300-400 MeV. That's basically the ranges one would get. So T freeze out is of order maybe 150 MeV, while T0 is about 300 or 400. So we know that from this estimate that the medium produced is produced above the crossover in a state which we would call quark-gluon plasma. That's why heavy ion collisions can be used to study quark-gluon plasma.
Sorry.
Yes.
These are the hydrodynamic equation after the collision, right? When
Yes.
the expansion occurs and we have this cooling because
Yeah.
of the volume expansion. But can we model the collision itself? I guess that the pressure or the energy will increase exactly at the collision, no?
Yes.
So can we model this?
Well, we can talk about energy. We can talk about charge density, but we cannot talk about pressure until equilibration happens. Remember, pressure is basically like entropy is a property of equilibrated system, right?
Okay.
You can talk about stress tensor, which is not going to be isotropic and everything, but if you want to describe the system using equation of state, in which pressure is a function of energy density, the system has to be equilibrated, right? So
we cannot define the pressure before the collision?
no. You can define something and call it pressure, but it won't make it so. Right? Because it's essentially a thermodynamic concept. There are concepts which you may find in literature which are called longitudinal pressure or transverse pressure, but this is just a name for things like a TZZ component of the stress tensor, right? So this is basically stress, right? Remember that in equilibrium, Tij, the stress tensor, has to be a diagonal unit matrix with a magnitude equal to pressure, right? So until then, you cannot define what pressure actually is.
But if we want to model the evolution of the pressure during the expansion, we need to know the initial condition for the pressure.
Yes.
At the collision.
Yes.
How do we get this?
Well, that's the biggest question. We have to assume something in order to get it, or the way that so this is just an analytical model. Of course, the field has progressed that now we can model. We do not need to assume the Bjorken boost invariance. We can just start with some initial condition, right? So the way that and then there are many assumptions which go in. First of all, how does this initial energy density gets generated? I wasn't planning to talk about it, but since you asked, the usual one of the sort of dominant pictures is the following. We know very well from experiment what happens in the collision of single nucleons, like proton-proton collisions, right? So you model the initial condition by using that information. So you assume basically that the protons and neutrons in the colliding neutron just collide independently, as if there was just individual collisions. The only thing you add is that, well, there's a probability that they pass, there's probability that they interact. This is treated by a model which carries the name of Glauber, if you heard, it basically estimates that it collides the nucleons with a given probability. After that, they generate some particles. There are models which describing nucleon collisions, which are very well tuned because of the experimental data, right? They are not first principle models. They are based on very often QCD string being stretched between the two quarks and then breaks, creating hadrons. That kind of naturally produces this sort of boost invariant picture from breaking of the string. That's how usually it happens. So once you have produced these quarks and gluons, right, then well, you have some kind of interaction dynamics between them, which is sort of QCD, in the sense that, of course, it's not really QCD, but you know what the perturbative cross sections are. You can improve them slightly in the infrared in order to for this to make sense. So you have this soup of quarks which just evolve like a kinetic gas, right? Then at some point you decide that this gas is already equilibrated, and at that point you switch to hydrodynamic description. After that, you have just a hydrodynamic code, which evolves, right, using hydrodynamic equation, now with much fewer degrees of freedom. That's the advantage of hydrodynamics. There's just a couple of densities, and that's it. So you evolve hydrodynamics, then you have to decide when it should freeze out. Well, this can be also done in a variety of ways. One could also do something like, what is called afterburner. It doesn't freeze out immediately into particles, but these particles can still collide with each other. So you basically have on some freeze-out surface of constant tau, if you think in terms of Bjorken, you convert your medium again into a gas, but now of hadrons, right? And then you know the hadronic cross sections, they interact, and you basically follow the hadrons until they are free to stream to the detector. That's how the modeling is usually done. And there are different ways of implementing it, and they are all compared to experiments with different degree of success, and that's how it works.
The initial temperature can be much higher than 150 MeV, right? Just after the collisions can be. But this is a freeze-out temperature, right?
This is a freeze-out temperature. So the initial temperature is estimated by Bjorken, and it's confirmed is about 2 to 3 times that. That's the.
Why it cannot be higher?
Because that would require much earlier equilibration time. And already 0.5 Fermi is difficult to get in any kind of perturbative, quark gluon scattering, right? You need some kind of strong coupling in order to do this. So it's hard to imagine equilibration happening, let's say, at an order of magnitude shorter time scale, right? There are also some other measurements which I didn't discuss, which indirectly tell us what the temperature is. For example, direct photons. These are the photons which are emitted basically because the plasma is hot, right, like the sun. Stefan Boltzmann says that the intensity is proportional to T to the 4th. So therefore, most of the photons comes from earlier times, right? And by determining the intensity of that radiation, you can estimate what the initial temperature is. And that's an agreement with this estimate. There is another interesting observable, which is the elliptic flow. That's another twist on this scenario, which is due to the fact that the nuclei not always collide head-on. Most of the time, they're actually slightly off. And this region here is not only finite in size, but also not spherical in shape, right? And therefore, the gradients of pressure are anisotropic. So there is stronger gradient in a shorter direction, right? And therefore, the expansion accelerates the particles in this direction more than in this. And this is a very prominently seen in the data. So, but in order to accelerate, remember that the velocity is equal to the integral of acceleration, which is the integral of gradient of pressure over time. So in order to get enough acceleration, you need to enough time. That's one of the arguments one would use to say that against the, for example, proposition that, well, maybe this medium didn't expand and then freeze out. Maybe it was just created like this. Then how do you explain the elliptic flow? Where did that come from, right? The elliptic flow needs time to develop. And that is another way to estimate how long the collision. That's probably the main reason why we have to make this time shorter. Because if you start, let's say, at 1 or 2 Fermi, you won't get enough elliptic flow to match the experimental data, right? So there are many things which go into this. But I would say that Bjorken scenario is always a starting point of the discussion of heavy ion collision. Any questions? All right. So I have very little time, so I will just proceed directly to the. So the other topic I didn't discuss is resonance gas description. I just of the freeze out. Of course, freeze out. When you say that freeze out creates a medium which is basically in which particles are distributed in velocities and chemical composition according to Boltzmann formula, right? Is not completely correct because it assumes no interactions between particles, right? And we discussed there are interactions, for example, rho mesons, or there are significant interactions due to resonances. Luckily, there is a method to take this into account, which is called resonance gas model. So essentially, due to a quite famous work, let me just say what underlines that description. There's a paper by Dashen, Ma, and Bernstein, 1969. It has nothing to do, wasn't in the context of heavy ion collisions. However, it does give the relativistic description of the thermodynamics of a system with interactions which produce resonances, right? So it turns out that accounting for these interactions is equivalent to consider between the stable particles, is equivalent to considering the gas of stable particles and the resonances together, right? And that's what is done in order to model the freeze out. So you create at the final stage of this simulation, you create a gas of stable hadrons, protons, nucleons, strange particles, etc., together with their resonances, right? And then you decay resonances to those particles, and that's how you get the finite multiplicities, right? So I'm going to discuss this in the detail. My purpose is to connect this to phase transitions. So, and in particular, I will focus on a critical point. Why? If you think about the crossover, right? So the measurement of the temperature and chemical potential at freeze out tells you where you are on the phase diagram. But how do you know where you are relative to any phase transitions? Right? Well, I mean, you know the temperature. So what we know from experiment is that as a function of collision energy, for small collision energy, so this is what we sort of think the phase diagram might look like. For small collision energy, you start somewhere here, and then as increased collision energy, you go up like this. This is how usually this freeze out. So square root of s increases this direction, and mu decreases. Remember, this has to do with the fact that, in particular, that the more entropy is produced, and that dilutes the whatever baryons stop in that region. So, but suppose you froze out. You know what T is and mu is, but what is the? How does this information tell you how far is the phase transition? Well, critical point is special. At the critical point, we know fluctuations are large. So therefore, if you find a proxy or some way of measuring the magnitude of fluctuations, you can tell how far you are from the critical point. And in particular, in this scenario, that means that if you increase the collision energy, of course, things will change. You know, the temperature change, the chemical potential change, but they change monotonously. But if you measure fluctuations, you will see that fluctuations will be larger in some region of square root of s than away from it. That non-monotonous behavior is the basic idea underlying the search of the critical point. Now, what are the observables that we need to look at? Obviously, it would be nice to measure the correlation lengths, but that obviously is not possible. All you have is basically the particles, right? But you can measure fluctuations. You can think of an ensemble of events created with similar initial conditions as a thermal ensemble, which it certainly is a good approximation to it. Now, what are the fluctuations in this ensemble? Well, they depend on the equation of state, right? And the equation of state, as we learned, becomes softer near the critical point in the sense that fluctuations of a certain mode, which involves different variables in a certain ratio, becomes large, right? So if those fluctuations are reflected in the fluctuations which experimentalists can measure, then you can translate the experimental measurements into a statement about proximity of the critical point, right? If the and that's what one can do. A simple model which so typically what do experimentalists measure? Well, they in each event you can measure the well, let's imagine that we bin the momentum space. They can measure the momentum of the particle, right? Well, let's imagine we bin the momentum space and we draw a histogram, right? How many particles are with a given momentum, right? Typically, of course, it's exponential because it's with a slope which gives you what the temperature is, right? Roughly speaking, or energy over temperature. So one could measure quantities which are either the fluctuation of the total number of particles, or you can measure the correlation between the number of particles, so this is n of p, with momentum, or np, p, and the number of particles with momentum p prime. Right? These are the quantities. Of course, if you integrate over p and p prime, then you get just a fluctuation of the number of these particles, right, in a given. So, how is this related to the to, let's say, critical fluctuations? Well, that's something which is which requires a little bit. Obviously, correlation length has nothing to do with the correlation between the momentum of different particles, right? In fact, if you think about it, and the Bjorken picture is useful for that, so let's imagine that this is our spatial rapidity, or Bjorken rapidity, right? And on the freeze-out line, freeze-out surface, you need to multiply by tau in order to get the real distance here in the in the coordinate space. So if you have a correlation length in the real space, it would correspond to rapidity correlation in rapidities of something like psi divided by tau, right? So the question is how large this correlation length can get. That's the question which is the one which requires understanding dynamics of the expansion. Remember the following, that obviously correlation lengths cannot be bigger than the size of the system. So that's one limitation. But that's not what limits the correlation lengths. The system evolves, right? And remember that equilibration takes time. Equilibration near the critical point takes more time. That's what the phenomenon of critical slowing down is. So this is dynamical critical phenomena, which I wouldn't have time to talk about. But I will just tell you the following, that the equilibration time near the critical point scales. There is a dynamical scaling with the power of the correlation lengths. And that power for this is universal. And for this universality class, this power, which is called z, is close to 3. Right? So the equilibration times goes very quickly with correlation lengths. Alternatively, that means that if the system evolves fast, the correlation length simply doesn't have time to grow. In fact, you can estimate the maximum correlation length as a expansion time, which is essentially Bjorken time, as we discussed, like a Hubble time, to the power 1 over z. Because z is bigger than 1, this is much less than the estimate you would get just from the size. So typically you get somewhere, again, the power is universal, but the coefficients in front are not. Typically you get something between 2 and 3 Fermi, right? So given that tau is somewhere between 10 to 15 Fermi, you can see that this fraction of rapidity is roughly 0.1, 0.2. Right? So given that the total rapidity of the total rapidity is typically of order 5 or 10, depending on the energy of the collision, you can easily estimate it using the definition. So it's very local, right? So it doesn't extend through the whole system and nowhere near it. What is important is that remember that in the Bjorken scenario, the velocity of the particle, or rather the rapidity of the particle, is equal to its rapidity of its position, right? And therefore, let me call that rapidity yp, where p refers to momentum. It's a function of momentum, right? So it's 1/2 of log e plus pz divided by e minus pz, right? So that rapidity is approximately its position, right? So now, if all the particles had the same rapidity here, then of course we could try to measure those correlations between rapidities of the particle, but that's not what happens. Remember that there is a thermal motion. In each of these correlated volumes, the particles move thermally with different velocities, right? And that velocity typically translates into rapidity, thermal rapidity of order 1. That's essentially your resolution of spatial. You cannot tell, measuring the particle with a given rapidity, you cannot tell whether it came from this region. So let's say this is YP. So Bjorken says that there's just one-to-one correspondence, but there is a thermal motion, which means that the particles from this region, which carry some information about correlation, could end up anywhere within the rapidity interval equal y thermal of order 1. And that means that if you detected particle here, it might have come from here, but it also might have come from here, right? So therefore, direct measurement of correlation lengths is not really possible, but the magnitude of fluctuations will be proportional to the power of correlation lengths, and that's what experimentalists measure. Yes?
Is there any tracker information in these correlations?
That's not sufficient. I mean, any tracker is not able to resolve the distances involved here. We're talking about Fermis, right? The tracker could possibly resolve maybe microns, but not Fermis, right?
But
Is that what you're asking?
Right, yeah, but by the time it gets to the detector, I mean, I don't know what RIC or, like, I'm thinking of LHC, like you could get more information from the tracker, but I don't know about RIC or other.
Yes, but it's nowhere near the nowhere near this, and even basically you think that each right. So basically, the information which is available is the momentum of a particle. Of course, there's additional information which allows you to tell whether the particle came from what is called primary vertex, or it came later from the decay of some secondary. One could separate those, but these distances are much bigger than what we are talking here, right? They're almost like, macroscopic distances, right? So basically, what experiments measure is the moments, is the fluctuations and its moments. And one can think of the fluctuation of, one can model this fluctuations of the number of the particles, or a multiplicity of the particles coming from a given volume in the following correlated volume, in the following way. Imagine that you have a so the effect of what the effect we are trying to model or understand. We want to know what is the effect of this fluctuation of the some thermodynamic variables which occur which are correlated in this way and therefore very large. Well, the way you could model this is to say that for a given type of the particles, it feels that fluctuation in a sense that the background in which it lives changes. Well, the temperature changes, chemical potential changes, and as a result, its Boltzmann distribution also changes, right? For example, its effective mass can change. That's the right, and these changes, which are random, right, essentially increase the fluctuations, right? In addition to usual, let's say, Poisson fluctuations you will get because you have statistics. There are fluctuations which are due to the fluctuations of the background, but their magnitude. So there's additional contribution here. So if you calculate delta n squared, for example, you will have a contribution which is Poisson, which is basically average n, if you wish, right? Plus the contribution which is proportional to the to the magnitude of the fluctuation of the of this underlying thermodynamic conditions, which we have calculated, right? And they are, you can they increase as you approach the critical point. They increase with the power of the correlation links. So if you know how the background conditions affect a given type of particles, you can calculate this coefficient here and its dependence of momentum. It can be done only in a very crude way today. However, that dependence is universal, right? And it tells us that the fluctuation should increase as you approach the critical point. Similar calculation can be done for the moments. This is a Poisson contribution. In the Poisson distribution, all moments are the same, and this will be xi to the power 9/2, right? And similarly for quartic cumulant, it also has a Poisson contribution plus some function of temperature and to the power 7. So you can see that the effect of the critical point on higher moments is higher. But as I already said, going to higher moments requires higher precision, more statistics. So in practice, these are the three which is being measured. And finally, let me just say what is the current status of the of these measurements. So the most interesting data, which is for the quartic moment of the proton distribution, or actually net proton, but that doesn't matter for low energies, collision energies, because most particles are protons anyway. If you normalize it by the Poisson value, right, you would expect the baseline to be essentially 1, right? If there is no no critical contribution, it should be 1 as a function of square root of s, right? Usually what is plotted here is some log, because you go over, you know, from 20 to 200. That's an order of magnitude. So, and it turns out that for large square root of s, that's what you will find. You find this, but then the points begin to drop, and at about 20 GeV, you almost get to 0. You know, it depends on acceptance cuts and everything, could be even negative. There are also error bars, right? This was the state of the initial measurements. Then that motivated going to low energies to see what you see afterwards. And let us compare this to what you see on the phase diagram. So this is temperature, chemical potential. This is critical point. Remember so this is the freeze out, right? Remember that the quartic moment has different sign depending on which direction you're approaching to the critical point. And if I remind you, along the crossover it's negative, right? So it has some negative contribution, negative values here in a cone, increasing towards the right, and then outside it's positive. So it's basically roughly that's what it looks like. So what would you expect then if you do the measurement? Well, first of all, you enter that. You decrease square root of s, right? So moving in this direction, corresponding to moving in this direction on the freeze out, you enter this negative region. So you get those negative contributions, right? Well, there may be other sources of that. For example, if you take into account the fact that proton number is conserved, there are some correlations which are also negatively contributions to this, which also does this. In fact, there are models, simulations which do not include critical point, which basically predict something like this. However, that's not what happens. When you measure smaller energies, you'll find that at 11 GeV it's somewhere here, and at 7 GeV it's somewhere here. Of course, the error bars at this point are still like this, and that's why we need and that motivates the further experiments, right? You want to reduce the error bars to see that this is not statistical, but if you just take this data at face value, it is very intriguing, right? Because that's exactly what you would expect here. Once you come out of this cone, the chaotic moment has to increase, right? It has to increase, and that's what seemingly one sees here, and this totally cannot be predicted by these simple simulations, which do not include the critical point. Of course, another interesting question is, when you come out of this region, this has to also come down. But that, of course, would require going to even lower energies, and that's why both Rick and experiments at FAIR and Nika are planning to also scan the lower part of the this collision energy range. Right now, Rick is collecting data at these energies to improve the statistics in order to basically to confirm or to eliminate this these signatures. So stay tuned. This is still the field which is in development. So yes.
I guess that if you go to very low energies, you recover neutron matter.
Yes.
So then there are more data for low energies.
The problem, of course, that when you go to this lower, then the question of many of the assumptions, in particular thermalization, become questionable. The system may be too small to talk about thermalization. So, but in any case, yes, there is a neutral matter, but there are no measurements of that kind. When people were studying neutron matter, they were not thinking about QCD critical point. The measurements were done, which were different measurements. Right? Yes? By that you mean at zero temperature? Or what do you mean along mu?
Or like in these accelerators, like can you do different isotopes or different size ions to like scan them? Or?
So different isotopes, yes. And there is a program at SPS which does this, but going not to heavier ones, but to lighter ones, right? Well, it turns out that the intuition is actually orthogonal to that. Changing the mass or the size of the colliding nuclei changes the freeze-out temperature, not chemical potential. And the reason is simply to understand the smaller system, as we already discussed, freezes out earlier for obvious reasons, right? And therefore at higher temperature, right? So yes, you can scan. You can. Well, this intuition, of course, is just the first qualitative. Of course, there is some dependence on mu, but the dominant dependence is on the temperature. So, yes, you can also do a little bit of a kind of strip here rather than just one line by changing the size of the colliding nuclei.
Like when you look at these programs, like if you just Google QCD phase diagram and then these different accelerators are like, it looks like they scan different regions. So how
Yes.
do they do it?
Different collision energies. So
But
the
you can only go along this dotted line.
yes.
Okay.
Yeah, and that's so typically the picture you would find in this case is a sort of slicing of the QCD phase diagram in the following way. So you have LHC somewhere here, basically, right? 0 mu, right? So this is LHC. This is what Claudia, I think, already written, so, shown. So Rick starts somewhere here, maybe at 15 or 20 MeV. So in the collider mode, it goes to somewhere around 300 or 400 MeV, right? And in the fixed target mode, it could go further. So this is Rick. This is Rick. Fixed target. You know, in the fixed target experiment, energies are smaller, right? For the same, right? And then, of course, there are experiments like FAIR or NICA. They cover roughly these regions, right? This is what you are, right? So this is what you would get, right? This is FAIR, NICA. It may be a little off, I would need to, but this is qualitatively the picture. Did I miss any other programs? I think there's also JPark in Japan, which also attempts to study a similar region of the phase diagram. So there's a high density and lower temperature. But the nuclei are the same, more or less. It's just the collision energy is smaller. Well, sorry for taking more of your time, but I really appreciate your attention and your insightful questions. And I hope to see you again at other schools or conferences. Good luck.